In today's video, we are going to learn about the concept of electric potential. If you recall, in the last lecture, we talked about electric potential energy. So let's see what exactly is electric potential. So electric potential is abbreviated as V. Electrostatic potential energy per unit charge. So if you want to have an equation, so we can write that electric potential energy per unit charge in the electric field is equal to electric potential. So basically we are saying that this V, which is electrostatic potential, is equal to U, which is the notation used for electrostatic potential energy per unit charge. Let Q be the charge. Well, this is how we get the equation. So from here, if you want to understand what is now between 2 points, what would be potential difference? That is electric potential difference. So suppose if you take I as initial point, it's a point in the electric field, initial point, and you abbreviate F as final point, any final point which is there in the electric field. And you want to know what is the difference, that is electrostatic potential difference. So this difference would be equal to Vf minus Vi. Vf minus Vi. So with this definition, this comes out to be what's the potential energy finally when you have this Q charge at the final position, what's the potential energy per unit charge minus potential energy what was there initially. So the potential difference, the electric potential difference between 2 points, initial and final, is the final potential minus the initial potential. And from here we know by the definition that we have here for the electrostatic potential is UF is the potential energy divided by Q minus potential energy initially that was there divided by U. So what we are telling here is, so from here we can write this difference in the potential is equal to, if you take Q common, we are saying that this is change in potential energy per unit charge. So we are saying that change in potential energy or the difference in the potential energy per unit charge is what is electric potential difference. So here this is giving you the idea of electric potential difference between 2 points, and that 2 points we have abbreviated as initial and final points. It's an extremely important definition. Electric potential difference between 2 points is delta U over Q. This can be abbreviated as delta V as electric potential difference between 2 points. Well, we can have this defined in terms of work as well, right? So this is between 2 points. And now let's define this in terms of work done. So having understood this concept, let's now try to understand in terms of work done. So I would drop this part here and would continue to derive a very important relation. And we know that this potential difference is equal to, we know that this potential difference, that is the potential energy difference, delta U, has a relation with work done, right? So it is negative of the work done by the, so suppose W we take here, W is work done by the electrostatic force on the charge to bring or to move it from initial point to final point. Well, so we know that this delta U has a relation. Delta U is equal to negative of the work done by the electrostatic force. If you replace this here in the equation, therefore we can write here for delta V, we can write it's going to be minus W over Q. So we can define the potential difference in terms of work done as the potential difference between 2 points is equal to the negative of the work done in moving, negative of the work done per unit charge in moving from initial point to the final point. So this is what we get, a very important relation of potential difference in terms of W. Now in case if suppose you consider a reference that is at initial point, the potential energy was 0, which means that if you bring it from infinity, so this is potential difference between 2 points. So at any point in the electric field, if you want to define what is electric potential, then if you reference this as potential energy initially was 0 at infinity. So we can have a generalized definition of electric point at any electric potential at any point in an electric field is going to be therefore electric potential at any point in the electric field as that point, any point in the electric field, as the electric field, the work done by the electric field in moving from initial, or that is from infinity to any point in the electric field. So we are getting this V, right? This V comes out to be now minus, if you indicate this work done in bringing the charge, the work done by the electric field in bringing the charge from infinity to a point in the electric field, and we have this work done per unit charge in bringing from infinity to a point in the electric field. So finally we get this very important definition of electric potential, and since we have this VF would become VI, that is VI is going to be 0, so we can write this as electric potential at any point in the electric field is the negative of the work done by the electric field in moving the charge from infinity to a point. So work done per unit charge. So if you make this, if you make this Q is equal to 1 coulomb, so we can write that this potential is equal to the work done in moving 1 coulomb of charge or a unit positive charge from infinity to any point in the electric field. So here, taking these examples, we can have a very clear picture of what exactly is the connection between all these quantities that we learned about. So if you want to get the unit for this, so it's going to be this joule. So therefore, the special unit, so this unit is, this work done is joule. So we can write this joule, and this Q is 1 coulomb. So you can write 1 joule divided by 1 coulomb. And this is going to be the SI unit. And this is actually is 1 volt. So in honor of the name of the scientist, this is this joule per coulomb, 1 volt, which is 1 joule per coulomb. This is known as 1 volt, and we can have this SI unit as 1 volt mentioned anytime. Well, this is in general the SI unit used. However, in the measurement in the domain of atomic and subatomic levels, so there is convenient energy unit measurement when we use the domain of atomic and subatomic levels, and that is known as electron volt. So having understood this, so take down these steps and take down this energy unit electron volt definition as well, which we'll be using them in the numerical problems when we have such situations defined in the measurements of atomic and subatomic levels. So 1 electron volt. So that is the unit that we use in the energy unit, 1 electron volt. Electron volt it is. Well, so how do we conceptualize? If you look carefully here, we got this from where? We got this from this minus W is equal to what? Delta U, right? So we can have this unit. This is this delta V is equal to minus of W is basically this, right? Delta U over Q. So basically this potential difference on the energy, or the energy, is equal to Q times delta V. So from here we get Q times delta V is equal to potential energy difference in potential energy between the 2 points. Now using this, we'll define this electron volt. So this electron volt is, it's that energy which is required to move this elementary charge, single elementary charge, from one point to the another through a potential difference of 1 volt. So the energy required, which is equal to the work done, the energy required the energy which is equal to the work done that is required to move the single elementary charge, and that is the single elementary charge E. Single elementary charge E is that of electron or proton, right? Electron or proton. So you are moving, so I'll write this definition here. It's the energy equal to the work required to move a single elementary charge. Single elementary charge. That is the charge of electron or proton through a potential difference of 1 volt. This is how we define electron volt. So what we are saying is that this 1 electron volt we are saying that 1 electron volt is equal to this elementary charge times 1 volt. That is what we are saying. Now this is the charge and this is the potential difference, right? 1 volt. We already know this equation is defined as delta U over Q. So if you bring this here, so it becomes, since Q times delta V, it's Q times potential difference is equal to the energy difference, that is the potential difference in potential energy. So that's what we have written. This is energy here, and this, if you multiply the charge with the potential difference, so this is the charge and this is the potential difference through 1 volt. So it is the energy equal to the work done to move a single elementary charge through a potential difference of 1 volt. This is what we are getting. So we can convert this into energy. Why? Because this is equal to delta U. So basically we are saying this is what it is equal to, right? So elementary charge, we know it's 1.6 times 10 raised to the power minus 19 coulombs, and this is 1 volt. So 1 volt is 1 joule over 1 joule over 1 coulomb. So we get this coulomb and here coulomb cancel. So therefore 1 electron volt. So therefore 1 electron volt comes out to be 1.6 times 10 raised to the power minus 19 joules. This is what we get as a result, and 1 electron volt. So this energy conversion is very important that we will be using in numerical problems. So this conceptualizes the entire the relations between different quantities, the potential energy, work done by the conservative force, which is electrostatic force, or the electric field, and what's the relation with the electrostatic potential. And the units that we have discussed is the SI unit, which is 1 volt, which equals 1 joule over 1 coulomb. And we have also discussed about the energy unit, convenient energy unit, electron volt, which is generally used in the measurements at the atomic and subatomic level, and how that's defined. So this ends up with this concept. And now we are going to learn about, in the next video, to find the electric potential at a point when we have configuration of different charges and different arrangements are there. So watch the next video for that concept. Thank you.